Let's do a few more examples about molecules that will have polar bonds in what is the molecular geometry. So another molecule that you often see in your, say, gem classes is take ammonia. Now, that's ammonia. The molecular formula, well, it has, that's the Lewis dot. But let's say nitrogen has 5 valence electrons. So I'm going to have a lone pair and 3 bonds like that. Remember that each of the bonds, you have 2 electrons here. And so you can count for nitrogen 1, 2, 3, 4, and 5. And the other 3 electrons are coming from the hydrogen. Now that's your Lewis. Then we need to determine the molecular geometry. Now, one aspect, we do have polar bonds. There is a difference in electronegativity between hydrogen and nitrogen. But we need to see what is the molecular geometry to be able to determine if the molecule is polar or not. Okay, so now what are we doing? Let's determine how many electron domains we have. So I'm going to circle the domains. One, that domain is lone pair. Let's do 1. Then I have another bond, 2, 3, 4. So I have 4 electron domains. Therefore, I'll be starting my drawing thinking in a tetrahedral structure, similar to what I did in the case of methane. So let's redraw methane. Here, carbon. 4 domains, 4 electron domains, which are bonding domains. For bonds, tetrahedral structure, and that is the angle. So now we're going to start doing this something similar for the nitrogen, but in this case, I'm going to say I'm going to put a nitrogen here at the center, and now I have all these domains. So here I will have 1, 2, 3, and 4 electron domains. I can put, for example, in one of those domains, I'm going to have the lone pair. The other 3 domains are going to have hydrogens. Now, this molecule is like this. And so 3. And it's not planar, so we call the geometry trigonal pyramidal. So let's write that down. This is trigonal pyramidal. That is tetrahedral, methane. Okay, now, together, polar bonds, they do exist. And so between, let's draw arrows pointing to the more electronegative atom. So more electronegative is on that end. So here, nitrogen is more electronegative than hydrogen. So I'm going to draw arrow, arrow, and arrow. These 3 arrows add up, and the resulting vector is pointing like this. So those vectors do not cancel out, so the molecule is polar. Okay, let's do one more thing. So we have determined that water is polar, ammonia is polar, methane is not. Let's try something else. Now another molecule with different geometry. Let's think of carbon dioxide. Drawing the Lewis structure is my first step. Central atom is carbon. And remember that we're trying to aim at complete the octet. So the Lewis structure with the dots is this. And if you count electrons around the central carbon, you have 2, 4, 6, 8. So octet is fulfilled. Here at the oxygen, 2, 4, 6, 8, same. 2, 4, 6, 8. So that is my Lewis structure. Now, how many domains do we have? So what in the first place, let's do polar bonds. The oxygen is more electronegative than carbon, so I'm going to draw an arrow pointing in this direction. I still don't know the geometry, but we're going to discuss that in a minute. So a couple of polar bonds. So is the molecule linear, yes or no? Well, the answer to that is you're thinking the valence share electron pair repulsion. You have 2 electron domains. So here you call this one domain, and this is another domain. So 2 electron domains. To be as separate as possible, they need to be at 180 degree angle. and that is precisely aligned. Let's draw, if we have, let's pretend this is a good circle, and that's the center. So the whole circumference, that's 360 degree. If I divide this like in half, that's 180. So that will be the angle here. But I have, the geometry is linear, but I have two polar bonds. Now the two vectors have the same magnitude because there's the same difference in electronegativity between carbon and oxygen in opposite, same direction, opposite directions. So here we have the two vectors cancel out, and because of that, we say this molecule has zero dipole moment, so it's non-polar. The molecule, it has polar bonds, the molecule is not polar. That has an impact in the intermolecular forces. Now let's do one more molecule here, and then we're going to be starting doing problems. So I'm going to erase methane. Please remember that methane is not polar because, well, in any bond, any molecule, hydrocarbon or not, but if it has carbon-hydrogen bonds, those bonds are simply covalent. We're not going to consider those polar. The difference in electronegativity between carbon and hydrogen is very small. Now we're going to do another molecule. The molecule this time is SO2, so sulfur dioxide. So I'm going to start putting the sulfur in the center, and I'm going to do this, my Lewis structure. Now, sulfur has, it is under oxygen, so it's 6 valence electrons. So here you will have a lone pair here. Difference to carbon. Here we didn't have a lone pair, here we do. Total number of electrons if you think each of these bonds is 1, 2, 3, 4, 5, 6 electrons coming from the sulfur. And now I'm going to do the lone pair of the oxygen. Now that is a Lewis structure. And now let's think of what is the best part. What is the geometry? Now let's think of the domains, electron domains, which is what we did here. So I have one electron domain, another surrounding the central atom. I forgot to say that. Around the central atom, there's 3 domains. So I need to place them. How? Well, let's do, this is my circumference. And now I'm going to divide that in 3 parts because I have 3 bonding domains. Let's say, similar to what is, say that we have BF3. Boron has 3 valence electrons. So the Lewis structure of this, oh, these are fluorine. So boron trifluoride in my example, and I was drawing boron. So that's a Lewis. Notice the difference. Here I don't have that. No lone pair. Here I do. Here I have 3 domains, but these are bonding domains. So in the bonding domains are the ones that we're going to be seeing for that geometry. So in the case of for boron trifluoride, let's do my circumference. That's my center. So I'm going to divide that in 3 equal parts. So this is 120 degree. So the geometry here is planar, but it's all the 3 atoms are in a plane. So we're going to say it is trigonal, so 3 bonds, right? Trigonal, planar. All right. But what's the geometry now in this case? For the case of sulfur, I'm going to erase my periodic table to be able to continue the drawing. I'm not going to draw the molecules. This contrast, they say BF3, we're going to contrast that with the other geometry, sulfur dioxide. So now I have 3 domains. So I'm going to start doing the same thing I did for the boron. So let's say that now I have this circumference, 3 domains. So yeah, I'm gonna do 1, 2, and 3 domains. But one of these domains is actually occupied by that. The others are occupied by bonds. So my actual geometry is the following. In this is actually, well, we can draw that for sulfur, but there is another structure that we can draw that will actually, because here, sulfur can expand the octet. And so 2, 4, 6, 8, 10. Here you have 10 electrons around. You can do that with sulfur because being in the third period of the periodic table, it will have the orbitals. So for those, you can expand the octet. I forgot to say that. You can draw also a resonance structure here that would put sulfur in the electrons here. But now, here you have a net charge. Notice that here you will have this. Now you have another resonance structure, which is not the topic of this video, but it's okay. We will have another. So that all of the 3, meaning I can represent this actually like partial bonds. But the point is that what is the geometry? The geometry is actually bent because these 3 atoms are not linear like it's here. And they're not because of the other domain, which is occupied by a lone pair. So see the difference here. So water was bent. The sulfur dioxide is also bent, so lone pair play a role. Let's distinguish between BF3. BF3 had 3 bonding domains. The geometry is trigonal planar. In ammonia, you have 3 bonding domains, but you have 1 non-bonding domain, which is a lone pair. So you need to start counting all of the domains with lone pairs or the bonds. Place them around the central atom to determine the geometry. So notice again the impact of the lone pair. This is trigonal pyramidal, this is trigonal planar. And carbon dioxide is linear, sulfur dioxide is bent.